Hello, today we are going to be starting our first video in our Gen Chem series, and we're going to be looking at atomic foundations. So we're going to go all the way back in time to the very first day of Gen Chem, and we're going to be looking at kind of the structure and organization of the atom, kind of basic topics like atomic weight, atomic mass, and then finally, we're going to touch on kind of electron orbitals and look at some kind of key intuitions, like physical intuitions that I want to build upon in later videos. So let's get started. Um, the first thing I kind of want to look at is, yeah, the structure of the atom. So there are really two structures that make an atom. And the first, of course, is the nucleus. And the second are the electron orbitals or shells. And within those are the three subatomic particles. So these are the three kind of particles that are smaller than an atom, subatomic, that make up the atom. And the first one in the nucleus is the proton, and the other subatomic particle in the nucleus is the neutron. And those are named after their charges. So a proton is positively charged, and a neutron is neutrally charged. And then that leaves, of course, the electrons and the electron orbitals. And they are negatively charged, equally and oppositely negatively charged to the proton. All right, so one other quick fact about the subatomic particles is that protons and neutrons have an atomic mass of 1 AMU, so one atomic mass unit, which really means that they are 1 gram per mole. And electrons have essentially a negligible mass. Okay, so that's an important fact. We'll come back to that. Now I want to kind of zoom in on this. And I guess I kind of gave it away already by showing on the right, but hopefully you can maybe look at this kind of simple 2D model of an atom and figure out what element it is. And that's okay if you can't. If you can't do that, the way to do this is to look at the number of protons. So this atom has 6 protons in it, meaning it has an atomic number of 6. So when you look at the periodic table will always have two numbers. It'll have a smaller number and a bigger number. And the smaller number is always going to be the atomic number. So this is our atomic number, and it is always equal to the number of protons. Always, always. So that is what makes each element distinct from another. So the reason carbon is because it has exactly 6 protons. If it has one more or one less, it's a different element. Okay, so then the second number is going to be the atomic mass. Atomic mass. And the atomic mass is the total mass of all of the subatomic particles. So adding up the masses of the proton, the neutron, and the electron. And so that's where the mass that I mentioned earlier comes in. So we said that protons and neutrons, they have a mass of 1 gram per mole. And electrons have a negligible mass. So really, the atomic mass tells you the total number of protons and neutrons. So if we're looking at this kind of carbon atom over here, we can see it has six, or actually, sorry, that's 7, but meant to have 6 neutrons and 6 protons. So if it's got 6 protons, that's how we know it's carbon, and the 6 neutrons is going to give it an atomic mass of 12. But then you might be wondering, why is the atomic mass of carbon 12.02 if this is 12? Is that because the 0.02 is like that negligible mass of the electrons I said earlier? Actually not. Those really are basically negligible. The reason that there's a 0.02 is because there's isotopes of carbon. And so isotopes are carbons with different numbers, or any element with different numbers of neutrons. So this is a carbon 12 atom that I have drawn. But if I add another neutron, so if I add 7 neutrons total, that makes it carbon 13. And the reason on the periodic table that the atomic mass is 12.02 is because the vast majority of the carbon in the universe is carbon 12. But there's a small fraction of carbon 13. And so the atomic mass on the periodic table is the average of all the isotopes. So as far as I know, I think carbon only has 12 and 13. There might be 14, but many other elements have many more isotopes. Some have like dozens. Um, and their atomic mass is basically the average of all of those isotopes. Okay, so these are the isotopes of carbon. And that just means you're changing the number of neutrons. Okay, now the next topic I want to kind of look at is I want to spend a bit of time on the electron orbitals. The electron orbitals are by far and away the most important kind of part of the atom. And I kind of want to start by focusing on this two-dimensional structure. So this two-dimensional structure of the atom, we can see that we have two orbitals, but I'm actually going to use a different term for them now. Instead of calling them orbitals, I'm going to call them shells. So this first shell is my inner shell. And you can see it has 2 electrons in it. And then I've got a second shell, my outer shell. And I'm also going to call it kind of the valence shell, or it's the shell that has the valence electrons. That's the most important term here. So the valence electrons are in the outer shell. And the reason that this outermost shell is the most important is really two things. One, the valence electrons participate in bonding. So only the electrons in the outermost shell, the valence shell, do bonding. So these are the electrons that will actually make molecules. And the other reason that's basically kind of related is that they are the highest in energy. And we're going to talk about this quite a bit more. But I want to kind of pause that and kind of think more about how the two-dimensional structure that I have written isn't really accurate, though. So changing gears for a second, I want to talk about how, of course, in real life, atoms are three-dimensional, just like everything. We're not like flat Stanley in real life. So this is a very simple and kind of reductive picture. So to really get a better sense of how electrons kind of exist and how they live, we need to think about 3 dimensions, right? Because it's not really so simple as electrons just kind of orbit in a circle. Really, within these shells are actual orbitals. So the shells are a simplification, and the truth is that electrons live in pairs, so they always are kind of buddied up in a pair in orbitals. And there's many kinds of orbitals. So scrolling down, there's actually 4 different kind of, I would say, like flavors of orbitals, and 3 of them are shown here. We've got the s, the p, and the d orbitals here. The 4th one is the f orbital, but that f orbital is really only reserved for for the larger elements, kind of at the bottom of the periodic table, and we're not going to worry about that. So the s, p, and d orbitals, like I said, there's kind of 3 flavors. And really by flavor, I mean there's 3 different distinct shapes here, right? So our s orbital, S is kind of for sphere, is how I remember it. It's our spherical orbital. We've got the p orbitals, which kind of have this dumbbell shape. And then we've got the d orbitals, which for the most part kind of look like eggs in a carton or something. Or they kind of look like 2 p orbitals, is kind of maybe the other way to think about it. And the other thing you'll notice is there's only like 1 s orbital, there's 3 p orbitals and 5 d orbitals. And that's because the shapes are different, right? So for the s orbital, it's just a sphere. There's really only one way to make or draw a sphere, right? Whereas if you look at our kind of figure 8 dumbbell shapes of the p orbitals, notice that each of the 3 are facing kind of in a different direction. So you've got one that's kind of like vertically placed, you've got another that's kind of like horizontal, and then another that's kind of like depth. Um, and so that's that kind of 3D component. And then when you go down to the d orbitals, you'll notice that there's kind of all sorts of directions. Um, and that's really the key thing about the distinction between shells and orbitals. So electrons, they actually exist in a 3D space and they live in these orbitals with 2 electrons each per orbital. Okay, we will definitely be talking about these more in a later video. They're really important, and I'll have a video on electron configuration that kind of goes into this more in depth. But now I kind of want to kind of conclude this video, wrap it up, by going back to what I was saying earlier about valence electrons being high in energy. So I really kind of want to take a step back and offer kind of an analogy, because what I really want to do in all these videos is help build kind of a physical intuition. I really want to not rely on memorization and build a physical intuition that you can rely on and be confident in going into your exam. So I want to talk about why these valence electrons are higher in energy. So let's kind of start by thinking of an analogy. So in a lot of ways, I kind of think of atoms as kind of being like little miniature solar systems. I mean, they kind of look similar, right? You've got something in the middle with a bunch of rings around it, orbitals around it. And in the solar system, you have the sun, which holds all the planets in orbit around it with its gravity. So the sun is really massive, so it has a lot of gravity, and it's holding all the planets around it. And I think the analogy to the atom is pretty good because you have the nucleus in the middle, and it's holding all the electrons in orbit around it with its kind of electrical energy. So instead of using gravity, obviously, what it's using is the fact that the protons are positive and the electrons are negative. So they're like super attracted to each other, right? It's also similar to magnets where you have like two ends that are lined up and are attracting each other. So that's what the protons and electrons are doing. And the thing is, imagine you are the electron in the inner orbital, right? If you're the inner shell electron, it means you're really close to those protons, which means that the attractive force is really strong. Just like if you were Mercury in the solar system, you'd be really close to the sun, so you'd really feel the gravitational pull of the sun. Whereas if you're the electrons in the valence shell, you feel less of that attraction, which means that you are kind of less stable in your orbit. It's actually easier to kind of pull you away because the attraction from you to the proton is smaller because you're further away. Um, and so that is the reason why those orbitals are higher energy, because if you're one of those inner shell electrons, it would take energy to kind of overcome its attraction, right? It would take energy for this inner shell electron, which is like really just wanting to get sucked into the nucleus. It would take energy to pull it out and to move it into the valence shell. That's why those outer shells are high energy, because they took energy. It took energy to get them there in the first place. Okay, so I'm going to kind of conclude there on that note, and um, I hope this kind of helps build up your physical intuition, and we're going to be talking about this a lot more as we move on to periodic trends and electron configuration. Okay, thanks for watching.